Welcome to the Structural Engineering Podcast.
We're your hosts, Zach and Max, structural engineers passionate about unraveling the complexities of our architectural wonders.
Whether you're a seasoned professional, an aspiring engineer, or simply fascinated by the science behind skyscrapers and bridges, you've come to the right place.
In each episode, we bring you insightful interviews with leading professionals.
So grab your hard hat,
or maybe your calculator,
sharpen your pencils, and get ready to explore the fascinating world of structural engineering. This is
the Structural Engineering Podcast.
All right, Max. So I want to let you know my brace frames are about to destroy your moment frames. Can I set it backwards?
You said it right. Yes, what you just said is going to happen, and I can't wait. What team are you on?
Core brace.
That shirt really speaks a lot. I'll say that you're wearing the winner's shirt right there. It's, I think, brace frame shirt.
Yeah, whatever. No, I'm on team moment frame today, and you're going down.
We had a bunch of conversations putting this together, and I realized when it was all done that we missed one important item. Now, we might have actually missed a few important items, but the one I'm thinking of is what is happening here. Zach and I, with the help of a coin, chose the best common R of 3 system to compare the weights and detailing required. These would be moment frames versus brace frames. So, choose your team, and let's get the conversation going.
I'll tell you the first reason. I was going to use this later, but this is why you're going down. The second thing when you look at moment resisting frames in ASC 7 in the table,
yes,
is steel special truss moment frames.
I did see that.
We're kind of integrating, trusses, which you can kind of walk that backwards into some braces.
Kind of a brace system. But that one, if you go to truss, you do get hit with an R point, right? Like that's only a 7. So it's like,
because it's
starting
so
from the get-go, because it's so bad, you have to drop it down a little bit. So I understand, but I see where you're trying to start.
Well, unfortunately, today we're not talking about seismic systems. We're talking about RF3. So,
yeah.
Ductility is on the argument line here.
We'll bring up a couple times. I'm going to talk about the R values, omega, and amplification, but the big one here is an RF3 system.
Yeah. So why don't you start us off and talk about the primary differences in the structural behavior between moment frames and brace frames?
Okay, so starting with the fundamentals, right? A moment frame, I'll start with the sillier one here, takes the force, the lateral force, out as a moment of the beam. So there's an axial force, and then the ends of each beam has a moment. It can impart that on the columns, and then the columns are often fixed base, but they don't certainly need to be. You can eat up a little drift that way, but you may have a fixed column, top and bottom, and then all that lateral force is going in bending action down to the foundation, right? So you have, and again, I'll say that I'm on team brace frame here. You might have a bigger foundation in the moment frame version because you're putting some bending in there as well as the overturning force, right? Brace frame, much simpler. You just put a diagonal number, and that obviously takes all your load. That could be in tension or compression, and you're just directly transferring it through. So, maybe the force coming one direction, you may be putting this through the beam up top. But if you have a single diagonal, your axial load on that beam, and then you transfer to axial load on that brace. So it can be pretty efficient.
It is efficient up until the point of which, an architect who we often work for wants to put windows around the whole perimeter of the building. And they don't want these ugly braces all over the place, Max.
Yeah, I've been working with a lot of really good architects recently, and they want to show the brace. So I do understand, but, it kind of depends on your crowd, I suppose. There is some such thing as an eccentric brace frame. That is getting into our higher R systems, right? So if you're using an R of 3 system, you don't need any AISC seismic detailing at all. And you can maybe make it eccentric on your own or have the brace land partway across the beam. So you can avoid a lot of window systems if they don't want a full width window. If they want a full width window, they get a full view of your brace. So I don't know if that's a win or lose.
That's a nice thing. I don't even have to think about it. Me being a moment frame just stands there. Now, my columns might be a little bit bigger, but at least it's not obstructing the whole window like your brace frame would.
Yeah. All right. So does that sound like a pretty concise way to split between them? Did I miss anything there?
No, I don't think so. I think that's good.
Okay. So I want to ask the next question here. How do the design considerations vary between moment frame and brace frame in terms of stiffness and strength requirements? And I want to emphasize stiffness here. I, being team brace frame, really focus on the stiffness available here, and we think it's one of our best attributes.
Well, if we think about it and we put, just a steel cable for your brace, and then my moment frame columns are W30s, well, you still might be winning actually,
Yeah.
because the stiffness of a moment frame is quite a challenge. Is actually probably, not to go against myself here, but it's probably one of the biggest struggles when designing a moment frame. A brace frame, trying to meet drift limits, not as big of a struggle typically. Now we're talking mid to low rise buildings. Once we go above that, it's a whole nother game. So I think for today's conversation, let's at least stick to low rise, maybe mid rise here. But so for a brace frame, super stiff system, everything is going through an axial approach. And so if you think about our stiffness equations, a lot easier, especially if we don't have very long braces and shorter base, to be more stiff, and thus the whole system to be that way. When we look at moment frames, though, we're taking things out through bending, as Max, as you already described. Bending a little bit more of a challenge for us. Your beams are a lot bigger than your columns, right? They're bending elements rather than an axial element. So since we're putting axial and bending through our columns, we're really going to start running into some stiffness challenges where our columns are going to have to be substantial. It's really the only downside, Max, of if we don't get into cost or weight or anything else. Or
we will. Don't worry. I want to ask real quick, just to go back on something I had mentioned. Your moment frames, when your office typically designs moment frames, do you lean towards a fixed space condition, right? Then you get a lot more stiffness for not that much more. Your foundation may be bigger, but it's not dramatically larger.
That's a good question. It really depends, as probably most of these questions we'll have to caveat with. If it depends on the height of the building, the amount of load going to the frame, if we're in high seismic or low seismic, kind of a lot of different things that are going on there. I would say for the most part, on our 1 to 2 story buildings, we're probably pinning the base. Thinking too of like how much load you're gonna, that transfer that moment into the bases can be quite challenging, from an anchor standpoint, base plate standpoint, amount of steel totals. So I would say we probably default mostly to pin bases.
Yeah. Okay. I agree. I have generally just done pin base, and it's for the same connection to the foundation. Can get a little crazy when you have to transfer some axial loads through the anchor bolt.
Let's throw the same question back to you, Max. How often are you fixing your brace frames?
So there's no problem they need to fix. Skip. You don't need to fix the brace frame, obviously. I think I do want to address it real quick that there is not really a condition where you need to fix the column of a brace frame. Where the brace intersects the column is partially fixed, but that is a direct force transfer to the base plate. You align those so that the force is going right through to the anchor center point.
Since we're on the topic of foundations and base plates and anchorage, what does the typical base plate look like for a moment frame? And then what could it look like if you were transferring 1,200 kips of shear and, let's say, equal amounts of tension compression through that base plate?
For a brace frame here. So typically, and I think I'm going to lose a point on this, is a brace frame anchor plate is typically a lot bigger because you need the gusset for the anchor, right? So you need the gusset for the brace to come down to. It's not adding a bunch necessarily, maybe a couple inches, but it's something you need to account for and just look at the geometry of that. So there's not any bending going through the base plate. The anchors is typically we just do a 4-bolt system. If this is a 1, 2, 3 story, light 3-story building, you can get away with just a 6. Oh, the magic of editing. And I misspoke here, so I'll just patch that. If you're looking at anchor bolts on the gusset side of your base plate, you very likely will have 6 compared to the 4 of your more traditional columns. Now, depending on the angle of your brace, maybe that goes to 8, but generally it's 1.5 times the alternate column for number of anchor bolts. For depth of bolts, it can get pretty deep as needed. A 2-foot long anchor bolt would be perfectly reasonable when you're transferring tension force here.
What about when you've got a lot of load, that 1200 kips max? What are you doing with the base plate? What's your techniques for that tension and shear?
We're transferring a lot of this to the foundation system, right? So we need to make sure that we can get the anchor bolt load into the rebar, right? So we have hooked bars, a splice length. A lot of times, that 18 to 24 inch, that was rounding a bit down. If you need to transfer a lot of load to the rebar, you can get a pretty long anchor bolt. Laterally, so if we have a serious whatever kip number you'd made up there, right? We will often do shear tabs. And that is a nice way to break some of that lateral load into the foundation. Beyond a shear lug, or shear key, just not shear tab. That's for beam. You're still just sitting on the
shear lug?
Yeah, shear lug. Beyond a shear lug, there are some cases where you can put continue the column underneath the base plate, right? So I've actually never done this, but I've seen this happen. So you can do a full penetration weld of the wide flange that you're using for a column underneath that base plate and just set that in the concrete. That is a little extreme, but if you're doing a tall building, that seems to be, I'm guessing, the way it's done. And then that's kind of it. Generally, it's just anchors. We have some high strength anchors available to us, but shear lug and I don't know. That's kind of about it. Do you have any additions there?
Yeah, so on the moment frame, I would say if we use what's commonly, I would say, seems to be the go-to, which is a wide flange column. If you're doing a pin base, I would say putting those anchors, and I believe is pretty generally accepted, putting the anchors inside the flange of that shape would kind of state that it's a pin base. I think that's always where there's some challenge to be stated, is every base plate can take some moment before it would ultimately fail. But I know once you pull those anchors out, there's more capability and capacity to be able to resist moment. So for a pin base, thinking 4 anchor bolts within the web and flanges. And then once we go to fix, you're probably let's just say an 8 anchor bolt pattern, maybe some stiffeners from your column to your base plate to make it really rigid and stiff. And then, you're just transferring that load out through the anchors, that moment, that shear, that tension. And then when you're getting really high loads, maybe you're looking at a breakout plate. So at the bottom of that anchor, those anchors underneath the bottom mat of reinforcing, you put a steel plate in there. So to be able to rip and fail out of tension, you got to engage all the bottom mat of reinforcing and maybe some additional bars that you'd add there. And then to take out, high loads of shear lugs like Max you mentioned are really common. There's some other options of dialing in more or less your base plate to the slab or your grade beam. And there's some funky things that AISC 341 has if you're really transferring out some wild loads and you want to prove that it's fixed or pinned. There's some options there. But I would say in general, for these shorter buildings, R3, probably looking at a 4 to 8 bolt kind of pattern. Pretty thick base plate.
Yeah, I have an edit to mine because I'm still thinking in my head just a small building, but you had put down a pretty high axial load that I need and shear load that I need to transfer. My 4 bolt situation is for an HSS, right? So this is for a light application column. That is not going to be the case with a wide flange. So I see why you were curious. That's definitely an 8 bolt system, but
I'm assuming my moment frame is just all wide flanges, no tube columns, just a wide flange system. Is that what you were assuming too?
I don't know.
Tubes for moment frame.
For me, it would be a tube system, certainly, right? For a moment frame, they tend to perform a little bit better as a wide flange. But if you're talking a 1-story building, it's going to look a little weird with a wide flange up there, right? Unless, if that's what's necessary, that's the route to take. But a 15-foot tall column probably should be a HSS 6x6 and get that pretty thick if you need it, but wouldn't expect it to be seeing that high of loads.
Yeah, I think to me, my initial thought with going to moment frames truly is just the efficiency of steel. We can really do a lot more if it's a wide flange, larger moment inertia with similar weights, but I think it all comes back to what's the specific scenario with respect to the architectural finishes and windows and cladding systems?
The wide flange, the moment of inertia compared to weight, is dramatically better because instead of putting a even thickness of steel around the whole thing, you're putting it only where it matters the most and then a little web to connect them. So, all right, I want to go into another one here. What are the typical construction costs associated with implementing moment frames compared to a brace frame? Now, I know that a brace frame is far, far cheaper, right? What do you think for the cost of these things? How do you compare them?
Yeah, so I've always heard, and I don't know exactly what systems this was compared to other than just a steel brace frame versus steel moment frame. So again, taking all the seismic requirements out, but maybe scalable still, that traditionally a moment frame is 3 times the cost of a brace frame to resist the same amount of load.
Three times the cost. Okay. And I read an article from AISC that says that the labor is about 2 times the material cost. Now, that is a difficult estimate to make, but to give you a scale of this stuff, the labor involved is a lot more costly than the material of just the frame.
Yeah, I think there might be some special systems out there for moment frames. Again, if you get into AISC 341 and go through all the different moment frame detailing types, there might be some systems that you're gonna find a little bit of difference too with that. But I think in general is probably a really good rule of thumb to use. But if you're on a project and you're looking at either option, I would say from research online and what other people are saying on inch tips per se, it really seems like most people try to drive towards a brace frame system and use the moment frame as kind of the backup. If again, just talking purely traditional buildings, I can think of some ideas of some buildings that aren't traditional where moment frames make more logical sense and are used way more often, where a brace frame wouldn't make any sense. One place I was reading about that moment frames and then cantilever columns are used a lot is like an outdoor, God, what do you call it? Not a pergola, would be like if you go to your park and you there's an outdoor cover, often
pavilion sort of thing.
Yeah, if you go to your park and there's a pavilion, those often don't have brace frames, if almost ever. And so whether those are cantilevered columns or moment frames, those are some traditional places where they seem to be more used. But on our 1, 2, 3 to 12-story buildings, it seems like brace frames are usually the ones that work the best.
That's what I'm used to as well. So on the drift elements here, how do moment frames and brace frames perform in terms of ductility and energy dissipation during seismic events? Now, I know we're not going to touch on the seismic code very hard here, but since we were just talking about drift, ductility kind of leans into that. How do you see these things performing? And I guess first off, let's start with the ductility factor. What do we have available for us for our system? After you, Zach.
Yeah, so for moment frames, a special moment frame is an R of 8, a steel special truss moment frame, an R of 7, intermediate 4.5, ordinary 3.5, and then we've got the R of 3 system or steel not specifically detailed for seismic. So we've got 5 options there to utilize when looking at what's our response modification factor or coefficient that's integral to our ductility, if not directly our ductility. Max, what kind of response modification factors are we looking for or looking at for brace frames?
So this actually is one element, probably the only element where your system moment frames are far better. We have a few options to us. I'm going to start with the 8 R of 8 systems, right? So eccentric brace frame, the BRB system, the core brace shirt that you're wearing right now. So these are R of 8 systems, and they are super ductile and very efficient, right? We pretty quickly drop down. So even our special system, right, which requires highly ductile beams, brace, columns, that's only an R of 6. We have a pretty low deflection CD, and our omega is only 2 here, but we walk down the street a little bit far. We do not have an intermediate system in a brace frame, right? So we just drop down to ordinary concentric brace frame. If we're going to look at that, that is a 3.25. Now, Zach and I talked before this episode, like when would you really use a OCBF versus just a R of 3 not detailed for size performance. There is a great article that we'll put the link in the show notes here, but give it a read in your opinion here, but I typically lean towards R of 3 systems. So that's what we have for us.
So one thing that I know we've talked about on the podcast before, but what is the deflection amplification factor? Why is there something I've got to multiply my deflection by?
If you have a really ductile system, you're probably also going to have members yielding, right? And so that amplification factor is to account for the yielding of items. So it almost is saying that, look how great this system is, right? It is a penalty, but it's a penalty because the yielding is so effective.
I don't think I answered this one that well, and again, I get to edit, so I get to add some detail here. You could look at deflection amplification requirements from a negative standpoint, sir, but it is directly accounting for the elastic response that we calculate and a modifier that picks up the yielding elements. I think about this as a handicap in the sports sense, if you're into that sort of thing. Our high R system has the privilege of this handicap because they take some serious yielding to shake off the force of the structure. We look at this in drift considerations because of the inelastic response of putting a giant load on a crooked column, sort of yucky. And we really don't want our buildings to hit each other. But other than those items, it's a small thing that is easy to address.
So what I remember from Emily Guglielmo was more so that your building is going to see the mass that it sees, and it's going to move because of that. We're saying you can design things for less because it's going to be ductile. So you're bringing your loads down to where, you're allowed to by the response modification factor, but then you got to bring it back up to the actual deflections it will see. So we're talking elastic versus inelastic behavior of the movement of our system. Max, why do we have an overstrength factor when it comes to our systems? What is the purpose of overstrength?
So I don't think I'm going to be able to define this extremely well. I don't think I can give the textbook definition here, but I always think of overstrength as making sure we can get the load to the frame, right? So the brace frame in my case, making sure we could transfer all the mass of the building through the diaphragms, down the collectors, and into the brace. How do you think about this?
Yeah, I go again to the elements that should yield and shouldn't yield. So we're designing the whole system for this reduced load, in which it's going to see more load, but we reduced it so we can make sure it's ductile and it yields. It actually is going to yield. So we're reducing what the load's going to be, but there's actually a lot more load on there. So we're going to take that and multiply it by 3 to make sure that the load path in certain areas are stronger and will not fail prior to the behavior we're looking for from whatever system we're utilizing. So common places, like you said, are collectors, cords. There are some elements within certain parts of the frame or the brace frame or the moment frame that have to be overstrength as well. And that's just to make sure that there's no way that element will fail, but you're pushing where the failure will actually occur.
Yeah, and I think you said that exactly correct, but that brought up to me, like, you know that this system is going to yield, and so it can see a lower force with a higher R value. But to make that load go to your frame, you have to make sure that the path is completely stiff and not yielding it, right? So you're just making sure those collector elements, that load can just transfer down that line without any bending of metal. I'm going to keep adding to this because not yielding is an okay way to think about this, but it's still not perfect. The R value lets you reduce the force based on the ductility, but the collectors, cords, connections, they don't know but that the brace is yielding. Surprise! So they need to be much closer to the elastic force from the mass of the structure, the stuff the earthquake is actually shaking.
So Max, for a brace frame, what are your typical limitations or constraint in terms of architectural flexibility and layout?
So yeah, you brought this up a little bit ago. It's a tough one, right? So unless the architect wants a brace in their window, right? Unless it's one of these really good architects that want to just put this in the center of their building, it can be problematic. There's a few things that we can do, right? With an R of 3 system, we can have what I'll still call an eccentric brace, maybe not concentric landing in the center or a single diagonal. We can go off on an axis. And if we are stiff enough and we follow the strength through the system, we're still providing an acceptable system, right? So we can miss windows, but we can't eliminate it. And so I always see this as the limitation of brace frames. If they want an open window system, that's not going to happen with a brace frame.
And again, that's only if it's at the exterior, right? Or interior windows. I mean, you could have a core out of brace frames.
Yeah, you certainly. Frequently. I've done a lot of cores out of brace frames and BRBs actually in this case. So it is a common one. And then maybe you have a system where you have a core of a brace frame and then your additional load is taken from your torsion is taken from moment frames at the perimeter. That has been done, I've heard.
Well, only because
Done a
they're
few of those.
superior.
Well, once you have the brace frame in the center, it's, really adds a lot of strength. Strength that you need as a moment frame. Kinda. I mean, the brace frame remains better, but ASCE would say the moment frame better be able to take at least 25% of the force in a seismic sense.
Man, isn't that true? It's like having a good friend,
Oh, gosh.
Yeah, so I think this is really my only spot to shine when it comes to moment frames. Is just the architectural flexibility. We can place them everywhere and anywhere and still allow for majority of that bay to be open, to walk through, to be open to the outside. I've seen for a lot of mid-size or mid-rise buildings that, there's a lot of bays that you're going to have moment frames of, where, you can probably get away with a little bit less brace frame bays because of the way it transfers loads. But yeah, when you want to get that open feel all the way around the building with the architect, moment frames are definitely the way to go. You might have a little bit bigger column, which might, hopefully your architect's exposing, because exposed structure, there's really no better.
Finest,
yeah. Show off the work that us structural engineers get to do. But that's really the only downside from an architectural standpoint, is that columns might be just a little bigger.
Yeah. I want to talk about redundancy factor real quick. We almost missed. This is getting into seismic territory, and this is not the point here. So this is just a short stepping aside. But when we're talking about drift of a moment frame, let's say this is in a seismic country, you're pretty limited to the redundancy factor. And I only bring this up, giving you some points, because the redundancy factor, this is worded very well in the code, of course, but if you just have a single frame on each side of your building, you're going to be hit with some penalties, right? But if you have multiple, like you were saying with your moment frame, you don't. And now with a moment frame, that's quite easy to do, because you could have several of the bays providing lateral resistance, but you also get hit with a pretty serious penalty on your drift. I think yours is about 1.3 times worse, or your limit is about 1.3 times tighter than my brace frame. So not only is yours more flexible, your limit is way lower. So it's kind of doubly bad. Seismic design category DEF only. I still think I win that point, but I wanted to make sure that's included.
Big columns, bro. You're not wrong there. You're not wrong there. I was actually looking into moment frames a little bit more, especially in the high seismic. I've only done them a few times, and it was a while ago, so don't do them every day. But there is a lot of other things you got to look at. Drift, just becomes a huge nuisance. This thing we like to call P delta, big problem. And the stability aspect of the building during moment frame, lateral loads during moment frames and stuff, there's a lot to consider. But when you get into designing, the behavior is very well understood. I would say it's easier to model the behavior of it than it is a brace frame, because there's a lot of things going on in a brace frame that it's just, trash.
I think the issue is the deflection is so small, it's just a hard number to read on the screen, because it's like 0.000. Your computer just cuts it off.
You're not wrong. So let's go here. What scenario or building types are moment frames generally preferred over brace frames? Continuing this thought of kind of the architectural influence.
Well, without taking a jab at moment frames here, if you want a open structure that's very flexible for future development, that is the place for moment frame, right? Because if you put a brace frame into a building, whether this is the core or the window, the perimeter, that can't go anywhere, and it's always going to be a problem. So they may change the way they want to develop this building. If you want to provide a building that is completely flexible to change however you want. I wouldn't cut any beams, but right, that's where a moment frame can shine because it doesn't really affect the layout of the building.
Yeah, I couldn't agree more. But I think that's where you typically see them. One building type that I've heard that they're in a lot is hospitals, right? Every few years, they're kind of redoing hospitals, relaying it out. If you have a good core system and you can utilize elevator and stair towers with, concrete shear walls or brace frame cores, moment frame cores, not really a great option because now you have columns in the weak axis and bending in the weak axis. You can all agree that's not a great load path.
Hospitals was actually in my mind too, because I've done a lot in that system, but I don't know why, but I guess they are moving. I think I'm just out of the time period of seeing hospitals change, but I suppose they do evolve over time and they want that flexibility.
Yeah, that. And then if you think of a hospital, it's a lot of glass. I mean, the exterior of especially like a bed tower, all glass, or a lot of openings, a lot of windows. Try and bring that light in. So again, I think a core system seems to be more common, or an exterior moment frame system. So again, like we talked about, you go to your parks, there's gonna be some moment frame systems out there. If Max and I missed a building type, you let us know. Shoot us an email, write it down in the notes or in the comments. Love to hear from you guys what you're doing with moment frames. It'd be really interesting to hear that. I know Max talked a little bit about having them at the exterior of your building to resist torsion. Is that common where you practice, or where else are you seeing them used?
So I want to ask about the connection of the beam to column in a moment frame. Now, this is an easy one for a brace frame, so I'll kind of just skip this. It looks like most other connections, right? It's pretty simple. There's a little bit of details that you have to look at, but let's look at the big connection here. A moment frame system, beam to column. How are you putting this together? Is this welded always? Can you bolt it up? What do you got?
Yeah, that's a really good question. And again, we're just talking about RF3 systems. So when you get to high seismic, which we've got episodes on where we've talked about it a little bit, and probably, let's say, some in the future that we'll talk more on, there's some very specific detailing for moment frame connections. But from an RF3 standpoint, where the code really kind of allows you the freedom to do what you'd like and just track the load path. What does that look like? As Max mentioned, the biggest thing with the moment frame, as we introed this, he said the beam is moment connected and transferring moment to the column, and then the column bends to the base plate, and that's our load path. So that connection is the most important part of all of this, because if you can't transfer moment, you no longer have a moment frame. You maybe have a cantilever column, and that's not the behavior we're trying to go towards. So let's say you can directly weld the moment frame to the column. Commonly that's done with the flanges of the beam. Again, we're just let's talk wide flange beam and wide flange column. You could directly weld that, and then there's some checks you need to do for any of these to make sure that the web isn't going to fail, and you don't need any stiffeners or doubler plates, web stiffeners, that is. So you can weld directly to the face of the wide flange column with let's say CJP, or fillet welds at a lower loads. Probably more common actually with fillet welds. You can do an end plate. So that's where you weld a kind of a face plate to the end of the beam, and then that bolts on to the column. There's stiffened and unstiffened end plates, just depending on how much load you're transferring. And then I think one part, if depending on how far you take some of your designs and where you go with things, is there's a level of fixity in your connection. So if you look at AISC 360, there's a fully restrained and partially restrained moment connections. And that's a great place to go to see all of them and more of them. But when you start trying to think of drifts and how things are acting, some of those connections might have a little bit more movement than others. And that's usually when you get into the nonlinear performance based, where you're trying to figure out the stiffness of the joint to be able to accurately depict the movement of the structure. So that can play a little bit. There's a great graph that shows the type of connection and then how much opportunity there is for rotation to occur that walks you through whether it's a partially restrained or fully restrained kind of system. It's also really nice that ASC 360 walks you through the typical connections for those. So again, I would say if you're going to do moment frames, I would go right there and look at what the kind of the typical options are. If you're doing a frame that is made out of tube steel, so HSS, fully welding that is the most common and probably the simplest way to develop your moment. There's a lot of checks of welding, or not welding, but transferring moments through the face of tubes. Again, another section of AISC 360 that you can go through and just make sure that you're not failing the face or the walls, or there's a few other checks that need to be done. But yeah, I would say very common, just welding, bolting, end plates. What else am I missing here, Max, from a non-seismic standpoint? Because there's a lot of pre-qualified seismic moment connections.
Yeah, I can't think of anything, but I was thinking while you were talking about that of the rotation allowed in a moment frame system, a special moment frame, intermediate moment frame. There is, so I'm flipping through the seismic design manual here, and there is a number. I can't quite find the page, but it's the radians permitted of rotation of the moment frame system. Ooh, I'll give you the one for intermediate moment frame here. The connection shall be capable of accommodating a story drift angle of at least 0.02 radians. Okay, Zach. So come back from a little break here. We have very similar, or not very similar, the same lateral load on a frame, the same height, the same width, and we're looking at 3 different dimensions. And, this is somewhere between practical, what would you use in a work environment, and what is possible, right? And I had a good feeling that my brace frame would be so much lighter, but I wanted to make sure that I'm showing what would actually be used here, right? So if I have a 3x3x1/4 that could work, my brace frame was an intention. So the compression K/R over 200, that didn't exactly apply. Tension elements for me, L/R of 300 is the recommended. So there is a little commentary on that, and that is unless it's a cable. But I have basically put together my 3 frames based on the loading that we had shared and pulled out the weight per linear foot, right? So how good can we do with our brace frame? And compared to our super heavy, super flexible moment frame that I think was maybe yours, is that all sounding good to you?
Yeah, once again here, I picked the losing team. Moment frames are drastically heavier, but I did find some interesting data that we'll get into as to what size the frame, from a bay size perspective, should it be to be most efficient for our exact loading and our exact scenario. I'd say anyone listening, it is kind of an interesting, and I would say this a lot more than brace frames, and we'll see this as we get into. There is definitely a really big sweet spot for moment frames that is going to help you significantly more when you're working your project. You should run maybe a little similar exercise to see what frame size is going to be the best option. And then, as we already discussed, moment frames being just pretty much the best friend of architects. You could work with them on getting a bay size dialed in that could be the most efficient to really get the most for your money when it comes to moment frames. As we already discussed, about 3 times the cost of brace frames.
Zach, before we lay out some numbers here, I was talking to Connor from Structural Python about this spreadsheet that I was making for this competition we have here on which is better, a brace frame or a moment frame. And I have a large Excel spreadsheet with a lot of complicated numbers, right? And it's trying to pull the lightest size members to make a brace frame work based on dimensions that I gave it, height, width. And when I was talking to Connor about this, he said, well, we could do a way simpler version in Python and it'll work better. So I'm on many hours of twinkling with this Excel, and it's okay, but it's not functional. And I wouldn't be able to pass it on to someone else, right? It is convoluted and confusing. But I sat down with Connor and we went over this maybe an hour. We put together a script with Python that I will be able to actually put on our website very soon. Once I make it through Connor's Python course, I'll have this nailed down. And I wanted to mention it since we're getting close to the launch day. Connor's async course is launching April, but only for people on the waitlist. Now, I can tell from my tutorial that I'll learn a lot from this course, but if you're interested in Python, for fun, or to make structural solvers, or to prove that brace frames are more efficient than moment frames to your podcast co-host, check it out at structuralpython.com, and I'll put the link in the show notes.
Well, on that, let's start the conversation on why moment frames are drastically better than brace frames.
It's on. Well, I'm on the edge of my seat here. I want to know what weight you have. Give you an idea of the systems again here. So we just have basically random. So 15 foot tall, a 10 foot bay, 15 foot wide bay, and a 20 foot wide bay. And trying to get a feel for how the steel sizes move as you shift. So our loading isn't changing. We have a 500 PLF dead load on our beam up top. We have a 1000 PLF live load on our beam up top. This is a made up number, but it's approximate to what we kind of see in real life in some circumstances. Let's start with our 10 foot, our smallest, our lightest. What's your pounds per linear foot approximately of a moment frame?
We're at 108 pounds per foot.
108. Wow. That's
So that's with HSS 6x6 columns and a W 16 by 26 beam.
interesting. Okay. And what drift were you holding those to?
So we thought, let's keep the building a little bit more flexible, kind of help us out here. So we're doing an H over 200. So really we're about 0.6 inches of drift. And one thing too I want to point out is we did use the 10-year MRI to get to that drift number. So roughly that 0.42 factor, which is in the commentary. I believe it's Appendix C. And if you go to the commentary, ASC 7, Appendix CC, it kind of walks you through this utilizing a 10-year MRI, which brings your loads down, and then comparing that to an H over 200 to 600 number, kind of depending on how your finishes react to movement. So that's kind of what we stuck to here. Again, when you're designing your own frame, so many different things to look into, but for us, that's the criteria we stuck to.
So my weight per foot compared to your 108 point, a big number, we're looking at around 47 pounds. I'll give you a 47.46589 pounds per linear foot here. It's a little less than half of what you got. Now, again, these are just baseline sizes, right? So we don't have a large system here that we need to make sure all the sizes fit well into.
So I think what was interesting on the mount frame side, as I continued making the bay wider and wider and wider, again, keeping the load the same, the height the same, is that I initially started decreasing in weight per lineal foot of the frame. So per the 15 feet and the 20 feet. So I got a reduction down to 80 pounds per foot, which is 25% less. And then at 20 feet, I got 76 pounds per foot. So 30% less if we're normalizing our 10-foot bay. And I thought, I wonder where this will stop. Will it keep going down, or when will it come back up from a bay perspective? Once I got to 25 feet, it came back up. So from 20 to 25 feet, I increased 5%. And then when I got to a 30-foot bay, which I would say is a pretty economical bay spacing for, let's say composite steel or a steel roof sometimes, I would say a pretty simple place to start is a 30 by 30 bay. I'm at 88%. So I am 12% less steel than my 10-foot bay per lineal foot of that frame, which from a 10-foot bay, I needed a W16 by 26, and to a 30-foot bay, I needed a W24 by 68. So significant increase just on that weight of the beam. Like, the same columns worked throughout this whole design. And another thing to note too, to reduce our drifts, I did fix the base. So there's going to be a little bit increased costs maybe in the foundations, the anchor bolts, the base connections, but trying to not go beyond a 6-inch column to hopefully, fit within the architectural space. I think another thing that would be interesting to look at is where do we fit in when we look at a wide flange column, right? Our drifts are purely tied to that moment of inertia of our system. And as we could have a wider column, it's going to be probably a little bit lighter potentially. The HSS is the 6x6 that I chose. It's about 27.5 pounds per foot. So from a wide flange perspective, might probably be the same. But then what we could get away from is fixing the base, having a pin base, a more simple connection to the foundation, as well as maybe a little bit less load on the foundation from not having to transfer moments.
Yeah, and I think also if you can make the decision based on the soil that you have available to you, if you have a high bearing value, you may want to lean into a fixed base because you're not going to go out to a massive foundation, right? There's a lot of cost in foundation.
So Max, tell me about the different sizes of yours. We just went over how moment frames change and the weight of that. How did you see that brace frames changed in weight per lineal foot?
Yeah, so I tried to hold my sizes to what I called an accurate size, which is, very tongue in cheek, is that I didn't want to give a beam that was unreasonably small, right? So we just have a beam that could size for bending and then also take the axial load. We organized our braces to take tension only. So I didn't really have to deal with compression from the original, where we started this sort of silly competition. But again, that is in the not reasonable approach. So in my accurate designs, I want to make sure it also included some compression. So I'm just giving all that backstory here for the size that I came up to. For a 10-foot brace that's 15 feet tall, and this is a weird dimension, I've got a HSS 4x4 by 3/8 working as a column. And let's see, my brace here is a HSS 4x4 by quarter. Now this is pushing into, that's pretty darn small. I wouldn't generally expect a 15-foot column to go to a 4x4, but for this case, this one is working for me.
Yeah. So Max, walk me through the increase of weights as you got bigger.
Okay, so we are starting with our 10-foot wide, 15-foot tall brace system. We're talking about 47.46 pounds per foot, or a total of 474 pounds. Right? Once we step up to our 15-foot wide system, we're not seeing a dramatic increase. And in the same way that you actually took a small step down, we also did, because a 10 by 15 frame is not the greatest shape, right? So in this one, we're getting closer to a square system, which is a little more efficient. We drop down to 41 pounds per linear foot. So our total weight is 620 in this case. And then as we continue to move, we make this a 20-foot wide brace. We're up to 44 pounds per linear foot. So we took a big increase in our weight. So now we're at 880 total pounds, but our per linear foot is just bumping up a little bit. And a lot of this comes from the beam size, right? Because now we have a beam spanning 20 feet holding the roof structure that we have sort of guessed awaiting here. But those are going to expand as you widen this bay. And then they're not taking that substantial of an axial load. So that isn't going to be a major consideration in the size of these.
Yeah, and I think to conclude all that, as there's already so many wins for you, this is just another one to tick off. I think the efficiency when it comes down to the things being loaded axially in lieu of bending is just so more efficient that I'm just never going to win. And I accept my failure.
Deal. Well, I'd say next competition you get to choose first. And I think I'll be losing, but
I think our next competition should be high seismic, and I get to pick the system for myself and for you.
Deal, yeah. I'm on the moment frame then.
We'll see. Maybe timber frame.
Oh gosh, yes, please. Okay, well, we have a clear winner. Brace frame is far lighter, about half the weight of the total system. So that's our ballpark that we can just work with as we make these decisions. It's going to vary quite a bit, right? And this is, I'll just say one more time, like this is made up numbers that fit a kind of typical system, but this is not based on a building. This is just our way to see how different are the total weights and how is that reflected in cost. That's it for this episode.
Thank you for joining us in another episode of the Structural Engineering Podcast. We hope you learned a lot this week on moment frames versus brace frames. And once again, I was defeated. We'll see you next week.